hello, good morning, good afternoon, good evening, wherever you're watching this from in the world. It's a pleasure to be talking at Search Solutions. Really nice to be invited, so thank you. Yes, so yeah, Martin's pretty much gone over everything already, but just a very quick bit of background about myself. I am from Glasgow. I did my PhD at Glasgow Uni. Leif, as a party, was my supervisor. And it was the process of turning me from this in 2013 to this in 2019. Bit of a joke there. Okay. And as of March this year, I'm a postdoctoral researcher at Delft University of Technology, working with Dr. Claudia Hoff in her Lambda lab. She's got seven highly talented PhD students, and we're all working on searches, learning complex search tasks, and so on and so forth. And the hope is I'm able to turn my user modeling expertise and so on and so forth that I acquired during my doctorate and apply it to that. But anyway, there's, as Martin was saying, I'm basically Elaine's laid the groundwork for me. She's also mentioned foraging theory as well, which is very nice. The stuff that was done at Park by Peter Paroli and Stuart Card. I think they published that paper in 1999. So I'm going to be talking about that extensively in this talk. Oh yeah, and also I did a little article for the Informer that I just wanted to shamelessly plug as well about what my experience has been in lockdown in the Netherlands. But anyway, whatever. Stopping behavior. It's a fundamental natural phenomenon. We all do it. We have to stop at some point, right? Whichever activity that we're doing, we have to say enough is enough. And of course, when we're searching, that also applies as well. We all know that search is very much an inherently interactive process. There's an expanding body of literature which suggests that people adapt their interactions with a ranked list of results based upon how they perceive the quality of the said list of results. And of course, they must be able to decide when they should stop examining that list of results and move on to the next one, right? However, I would argue that despite this importance for us to be able to understand why people stop examining content, there are somewhat a limited number of studies which have examined this phenomenon in detail. Now, I guess a little on a side point is that as of late, I've started to see an increasing number of articles in my Google Scholar recommended reading list that do mention stopping. So it's really nice to see that. But by and large, studies that have asked people, why did you stop examining content? The general sort of response from people is, well, I stopped because I felt that I had enough. I felt that what I found was good enough. Or some people would say that they're frustrated or whatever. But are those sort of vague sort of sentiments that people sort of echo in these user studies? Are they good enough for us as researchers when we're trying to understand and build better search systems? Obviously, the answer is no. We want to develop a better, more intuitive understanding of what's going on. And this is what I've been looking at over the past couple of years in my doctorate at Glasgow. Is like I've been running user studies, looking at empirical observations to try and see what happens to people stopping behavior under certain contexts, and trying to see whether or not these empirical observations match up with the theories that have been proposed over the years, i.e. in particular foraging theory, which we'll be talking about extensively. As a little bit of a caveat, I should also mention that the work that I've done has basically been looking at relatively simplistic search tasks, in the sense that we would task people to go on a fact-finding mission and find out, for example, which animals are going extinct or are endangered in the wild. There are lots of other different tasks that we could get people to search with and examine their behaviors and their stopping behaviors, but we haven't done that yet. I would love to do that in the future, because I'm sure that we would see different behaviors or different stopping behaviors being applied to different contexts. But this is basically just for ad hoc retrieval as such. So there are a large number of heuristics which have been defined by researchers over decades in a variety of different disciplines of science, from ecology to psychology to information science, right? And these heuristics try to sort of encapsulate why people might be inclined to stop examining results or looking for things or whatever, right? And what I would like to do is just give you some brief examples of two really, really simple heuristics, right, that we can employ. I've only got one screen here, so you might see all these pop-ups, unfortunately. I want to talk about the number and the give up heuristics. Very, very simple heuristics, which have been basically taken from observing how birds, little chickadee birds, behave when they're foraging for berries and whatnot in the wild. And this considers aspects and the models underpinning optimal foraging theory, which is the precursor to information foraging theory, or application of it to information science. So if you imagine the number heuristic is simple. You stop after you've found a certain number of items that you're looking for, right? It's a relatively simple strategy or heuristic or approach, but it could be quite flawed. So if you imagine you've got two trees, one with a nice juicy berry, and your little birdie flies in, your little birdie will go, I want to find one of these berries for each tree that I visit, right? If you can imagine, a little chickadee bird could imagine that kind of thing, right? It flies to the tree, finds the berry, consumes it, gains the energy from eating that berry, and then is satisfied, moves on to the next tree. But there's a problem. There is no berry in that tree. So what happens? If you were to code this up and implement it, you probably get stuck in an infinite loop because you don't have that berry available to you, right? This is like reciprocal rank. You keep going until you find what you're after, but it's flawed. So one of the strategies that was devised by looking at the behavior of the bird is like, well, maybe they give up after a certain period of time. They go and fly to the tree, they look for a berry, right? And after a period of time has elapsed, they might find a berry, and then they keep looking, and then they'll stop and say, okay, there's nothing else here. And then they'll fly onto the next tree. And if they don't find anything, they'll stop and they'll move on, right? So there's a variety of different ways in which we can encode this heuristic of stopping. And this is what we call an adaptive strategy, right? Because it adapts based upon what you're presented with at that particular moment in time, rather than a fixed approach, which I'll talk about later. And as I said, there's a variety of other different heuristics out there. They have been proposed from a variety of different fields. Some of them are listed here. I don't have time, unfortunately, to explain all of them to you. I would very much like to, but yeah, go have a look at my thesis. Shameless plug if you want to have a look at an explanation as to what each of these mean and what they do. But they all have different ways of working. And some, for example, like the mental list rule or heuristic, that might be applicable for a particular task like shopping, e-commerce. You might have a series of criteria that you want to find in a particular item. And if you can tick all of those items off in your mental list, then you might stop because you found that item that you're looking for, as an example, right? But there's lots of different applicable uses for these. Thinking about how we measure things as well in IR or interactive IR. Whether we want to evaluate a rank list of results from a system or we want to evaluate how people have interacted with them, there is some form of stopping model that's encoded within these measures, right? So the simplest measure that we can think of is precision at K, right? You go down to rank K and you stop, okay? So if K is 5, you look at 5 results and you stop. That's fine for simplistic things. We want to just evaluate how the performance of the system is, but it's not really representative of how people actually behave in the wild or in real world, right? Because if I went to a rank 5 for every query that I ever issue, I'm probably not doing it right. And indeed, that's not very intuitive. Oh yeah, that's an example of a fixed strategy, right? Because you're not adapting your behavior based upon what you see. Okay. But it's not very intuitive, as I said, because if you're given a set of results, right? And if we imagine that this little sort of funnel is of like highly relevant items at the top, and the further down you go, the more red it gets, which means that the results become less and less relevant or useful to you, and you'll be able to extract less and less gain from them. If you had a searcher which went to a very, very great depth and examined content that was non-relevant to what they're after and likely to give little gain, then they're probably going to be dissatisfied because they're behaving in a suboptimal way. Whereas if we had a searcher who stopped at a much higher or greater depth and they have an intuition as to, well, the content's actually starting to change and become less useful to me, they'll stop and they'll be more satisfied because they're able to stop earlier, they've wasted less time, and they'll be able to invest that time in perhaps reformulating their query based upon what they've observed and potentially get more gain. That's usually how it works. And this is basically what's called the patch model, right? So remember the little tree? right, with the berries in, that is basically what a patch is. And us as researchers in information retrieval, we model this patch as usually a SERP, right, a set of results. So instead of berries that a bird picks, we are picking out juicy results, which are going to be useful for us in terms of gaining and acquiring knowledge rather than gaining energy when we eat something, okay? And the theory suggests there's mathematical underpinnings and everything to this, but if you read Paroli and Card's paper from 1999, the theory suggests that the patch model, you get a gain curve, right? So when you enter a particular patch, you're gaining knowledge or value, whatever it is that you're trying to gain, right? So over time, you'll eat berries or read documents, and over time, that starts to diminish as you've consumed everything that's good. What the theory suggests is if you draw a tangent to the curve through the origin of that particular plot, right? And then pinpoint the location at which that tangent intersects the curve, that's your optimal stopping point, right? And that's the optimal time at which you should stop. Why? Because everything after that, you're getting diminishing returns. Your rate of gain is actually decreasing over time, but your rate of gain here is actually increasing, right? And that point and that curve is basically what all of these heuristics, which have been proposed over the years, is trying to approximate. Some are reasonably good. Some make you stop too early. Some make you stop way too late, right? But generally speaking, that's what these heuristics are trying to sort of pinpoint. And I did a number of different investigations over the years to look at which of these heuristics pinpoints that stopping point best, right? We ran user studies, and we used data from those user studies to ground a lot of simulated analyses, operationalizing different heuristics in different ways, and then taking those operationalized heuristics and then trying to look at the performance of them in terms of just overall performance, which one does the best, and compare them to real world user behavior from the user studies to see if one heuristic actually approximates behavior or stopping behavior more on point with what people actually do, right? So I do have some graphs here. I'm not going to go into detail about where I got them, like how I computed them and stuff, but these are just basically results of simulations that I ran, which are all reported in my thesis. But I just want to demonstrate what happens. So we have, just in terms of overall performance, we have the gain that users can acquire on the y-axis and the depth per query along on the x-axis, right? And what I'm going to do is I'm going to bring in a couple of lines which represent different strategies or different heuristics, right? And each point in those lines represents a given configuration. And behind each configuration, there are thousands of simulation runs. But what they basically point to is a particular level of gain that's acquired at that particular configuration at a particular depth, right? And the longer the line is along the x-axis, right, the deeper that these people will go on average when you increase the configuration value, whatever it is. And you'll generally find that the gain actually starts to drop off the deeper you go. Why? Because the deeper that you go in a set of results, the less time that you have to issue new queries, which means you're less likely to find relevant items at the top of a new query because you're just investing all of your time looking down at the bottom dregs of something that you've basically taken everything of value out of. So we could incorporate a basic fixed strategy, which means that people will always go to a depth of whatever, like so. So we can see like the highest level of gain one could acquire was about 2.6 at a depth of 7. I think that was like the optimal value. But you can see that people stop relatively short after 10. That's what I want to convey there. And if we bring in an adaptive strategy where people are able to adapt their behavior based upon what they see, using the frustration heuristic, which basically says, I'm frustrated after seeing X non-relevant items, therefore I'm going to stop and reformulate and issue another query. It's a very similar trend. If you were to break down the queries, if you were to break down and look at the performance on a per query basis, you would see that for poor queries, the fixed depth strategy does extremely badly because you will always go to the same depth. But the frustration strategy, the adaptive strategy, does really well because if it's a per query, you're more likely to stop really early on, right? That doesn't really reflect it there, but you do get an overall higher level of gain. But if we bring in a more complex strategy that doesn't consider a very simple heuristic, right? we see that, well, people go much deeper and the level of gain starts to tail off. So it's sort of similar at the beginning, but it drops off towards the end. And this is what we consider to be the term difference. I think we just looked at the KL difference, the KL divergence difference between a snippet versus previous snippets. You could argue that, well, people don't use KL difference in their head. That's a perfectly plausible reason as well. But it demonstrates that simple strategies seem to have the best performance. Okay, that's the sort of takeaway from this. And it's a similar sort of picture in terms of approximations. So we were able to take the mean squared error between the real world observations versus what the simulated models presented as well. If we plotted what people actually reached, the average stopping depth for real world users on this line here, on this dotted line, we can start to see that, okay, so the approximation is pretty good because the closer to zero it is, the better the approximation. And it's pretty close to what people actually achieved for a fixed approach. Frustration, similar kind of line. But then if we introduce a more complex strategy like term difference, the approximation goes a little bit awry. So yeah, there's some interesting results there. But the takeaway is that simple is best, from my findings so far anyway. It might not be the case for every scenario. So that's what happens within a patch, right? But what about the process of actually determining whether or not you should actually begin to examine the content in the patch, whether you want to fly into the tree into the first place, or whether or not you actually want to delve into the set of results that Google has presented to you when you've issued a query, right? So information foraging theory also has us covered there. We have something called the scent model as well. And I had this nice little illustration that I would like to show you. There we go, mountains. There's the Loch Ness Monster, okay. And there's two patches of land in front of us, all right, patch 1 and patch 2. And within each of these patches, there's different bits of food or things that we can gain energy from, right? And there's a little forager guy. And based upon the scent that each patch presents, we need to deduce which patch is the one that they're most likely to enter, right? Now, you know, from a cursory glance, given the fact that you have cues here, more paw prints from different animals, and there's just more food there available than this patch, you'd probably be thinking that patch 1 is the one that the forager would like to go into. And indeed, that is the case. Does this patch smell good? If it does, yes, I'm going to go into the patch and investigate. Otherwise, no, I'm just going to bail it, move on, and find something else, find a better patch. And if we model a patch as a SERP after you've entered a query, the time it takes for you to walk to that patch is basically you entering your query into the system. And then you have to sort of give yourself a moment to have a quick look, to eyeball, if you like, that particular set of results that's presented to you to see if there's any cues or images that might suggest to you that the search engine has understood your intent, and therefore the likelihood of the patch being good is higher. So you'd probably be more likely to say, I'm going to invest the effort subconsciously, I'm going to invest the effort to enter this patch and take a look, right? So we were able to operationalize that by taking data from a user study that I ran, right? And what we did is we looked at all of the queries that people issued, okay? And we were able to deduce whether or not it was a high scented page or a low scented page. We had a threshold that we took from a previous study. And we were able to group people, or we were able to order people based upon the likelihood of them interacting with a SERP, if it was a low quality page or a high quality page, right? And we could then start to split people up into different groups based upon these probabilities of interaction. We had our lower baseline, which meant that they would always enter the patch regardless of whether it was deemed to be good or bad. We had naive users who were found to be really bad at identifying the scent of a particular SERP. We then took the average of all of the subjects that we had available at our disposal. We had the top 15 users in terms of identifying content or identifying the scent of a page. And then we had our upper bound, our simulated model, which basically said, you will only enter this particular page and start examining content if it is deemed to be of high quality. Why is this important? Well, If you enter a SERP that is of low quality, you're wasting time, right? You're not behaving in an optimal way. You're looking at results in detail, you're investing time and effort reading stuff and trying to understand whether this is good or bad, when you could be doing your eyeballing thing and working out whether or not I should be making this extra investment in my time or not. So just to very, very quickly demonstrate a plot as well, we have our gain and the depth that people went to on average for each query, or per query rather. And if we bring in the cumulative gain as well, our baseline, you can see it's quite a stretched out line. People for the different configurations would go to greater depths and their gain would actually drop. And naive users behave pretty much just as poorly as our lower baseline. They were terrible at identifying relevant content and they would likely only enter SERPs that were of poor quality. But then as we start to introduce the likelihood that they would actually enter a SERP which is of high quality or higher quality, this gain starts to increase. And then when we start to introduce the users who are much better at identifying content or identifying SERPs that are of a high scent, therefore entering them, investing the time and the effort to find the relevant documents within them, we start to see a huge improvement in terms of the performance that's attained. Indeed, the savvy users, like I think it was an 80% likelihood, I think, from memory, that they would enter a SERP which is of high quality. And then obviously the 100% chance for the upper bound as well. So you can see that scent actually has a huge effect on how people search, on how people behave. And I think this is something that we really need to be considerate of when we're thinking about how we design our interfaces and so on and so forth. So just to wrap things up now, because I know that I've only got a few minutes left. I just want to talk very briefly about intuition and internalization as well. So we were talking about like gain curves and so on and so forth. I was like, do we really expect that people will be computing a gain curve in their head as they go through the set of results? No, probably not. And there's probably some kind of internal tolerance that's going on there, or some sort of, if I hark back to the beginning of my talk, intuitiveness, right? So there's lots of questions there that we need to address. And if I would just give an example very briefly, it's like if I had, this is from my thesis, if I had a ball, right, and I throw the ball in the air and I catch it, am I A, going to be thinking about the physics and the equations to try and work out when the ball is going to come back down to Earth and where my hand should be? Or am I B, going to be thinking about the proprioception system giving me feedback that I have at my disposal, i.e. I am a human being, I can use my intuition and my 30 years of experience on this earth to try and figure out where the ball's going to land. I think that the same basic principle is being applied here. People have relatively simplistic tolerances to non-relevance, for example, that we really need to take into consideration when we're thinking about stopping behaviors. Yeah, so to sum things up, it's clear that people undoubtedly have different strategies in terms of determining when to stop, and they have different tolerances to what is acceptable to them. And it's clear as well that we also need to be considering things like scent, because it clearly has an impact on how people search, how people behave. And it's clear that some people pick that up better than others, okay? Question of potential like research in the future is with different learning tasks, interacting with the system in different ways for different purposes, how would these behaviors change? How would the probabilities change? As I said earlier, I've only been looking at one basic task in particular. And how would biases creep into all of this as well? I mean, I've seen in study, like a study that I did, user study in 2017, where we examined the length of snippets. As we increased the length of snippets, people started to believe that they were making more informed choices, but actually that didn't turn out to be the case. It just made them more click happy. So maybe things like the sunken cost fallacy and so on and so forth could be having an effect here. And evaluation is also hugely important. Like, how do you turn a naive searcher into a savvy searcher? What can we do to help people? How can we design better interfaces? How can we give them cues on the screen to give them a better idea of what, when they're sniffing around for the scent, how can we help them with that? And, you know, as a sort of devil's advocate thing at the end, we've been thinking about behaving in an optimal way, but what if you actually want people to keep going rather than stop? You know, there could be things like finding ad revenue on things like Instagram or Facebook, where you want people to keep scrolling so you can put more adverts onto your screen. It's an interesting perspective as well. But I hope that that was just enough to give you a rough idea of what I've been working on. And if you're interested, you can have a look at what I've been, my thesis, and my email address is there if you wish to ask me a question, if you're watching this after the fact. But I'm continuing this work at Delft with an emphasis on more complex learning tasks. And hopefully we can get some interesting results from there. But yes, thank you very much. I hope you found that interesting. Cheers.